Hello. In this session we are going to continue our lesson about the notion of logarithm, and I will start introducing you this notion formally. We had some kind of motivation in the previous session, if you remember. Now we want to introduce the notion of logarithm very formally. So this is why I start with the definition of a logarithm. So consider real numbers a and b such that we have these properties. A is greater than 0, a is not equal to 1, and b is greater than 0. I'm motivated about these conditions if you remember in the previous lecture. The logarithm of b in base a is defined to be the unique real number such that when you raise a to that power, to that number, it becomes equal to b. So in other words, we say that log of b in base a is equal to x if and only if, it means they are equivalent, a to the x is equal to b. So it means that base raised to this number becomes equal to b. Okay? So if I ask you what is this logarithm, you would say this logarithm is that number, like x, so when I raise a to that power, it becomes b. So that's the meaning of logarithm. And it is extremely important to know this relation, this equivalency by heart. Before we continue, let me just give you a remark. If the base of a logarithm is 10, instead of writing log of b in base 10, one simply writes log of b. So if you see the base is absent in the symbol that you are using for log, it means that this base is 10. So when you see log of any number, it means log of that number in base 10. Okay. So this is extremely important. So if you want to see if an equality involving a logarithm is true or false, you translate it into exponential form, into its equivalent statement, and then use your knowledge for exponents to see if this new equality is true or false. If this equality is true, you say that this one is also true. If this equality is false, you would say that this one is also false. So for example, I'm asking you to tell me which one of them, if any, is true and which one is false. So if I want to answer, this is telling you log of 125 in base 5 is equal to 3. If I want to see if this is true or false, what I need to do, I need to use the definition of the logarithm. I would say that the log of 125 in base 5 is equal to 3. This statement is equivalent to this statement that 5 to the 3 is 125. Yes? This number is equal to 125. This is equality. This is an equality. It might be true, might be false. If it is true, we say that this one is also true. If this is false, we say that this is also false. But I think you immediately realize that this is a true statement because 5 to the 3 means 5 times 5 times 5, which becomes exactly 125. So because this is true, I conclude that this one is also true. Let us check the other one. So this log of 27 in base 3 is 4. This is equivalent to this new mathematical statement that 3 to the 4 is 27. But hopefully you immediately agree with me that this is a false statement because 3 to the 4 is not 27, it's 81. So then it turns out that this is false. So this means that you can conclude that this one is also false. Okay, as simple as that. Okay, it's very important to be able to translate these two statements together. Sometimes you are given this one, you need to be able to write this logarithmic equality in in the form of exponential equality, or sometimes you have already your exponential equality, you want to write it in logarithmic form. So you need to be able to go back and forth between these two representations. Okay, so now number 2 is actually mainly trying to improve your skill to be able to go from an exponential statement to a logarithm, to its equivalent logarithmic statement. Okay, so here you see that we want to solve each one of these equations and determine the exact value for x. Okay, so what can we do for number 1? So number 1 is very simple actually. So you see 2 to the x is equal to 3, and I am looking for this exponent x. Okay? So now if I want to find this x, it's immediately clear that I can compare this one with this one. Here 2 is playing the role of this a, and 3 is playing the role of this b. And as a matter of fact, I'm interested in this x, so I can write its equivalent, okay? So what does it mean? It means that from here I can conclude that x that is in the exponent is equal to the log of this number, which is 3 in this case, in the base of this number. So it becomes 3 in base 2. And that's it. This is your exact answer. If you want to find an approximation to this number, you can use a digital help to answer this, but that's not necessary for this problem because this problem is asking you for the exact value. So that's the end of the story. Okay, now let us go to number 2. So number 2, I have 5 to the power of 3x equals to 6. If you compare this one with that one, it is still comparable. Yes, so what you can do, you can see that A is 5 in this problem, B is 6 in this problem, but instead of having x, you have 3x. Okay, it doesn't matter. Instead of putting x here, you will put 3x. So this implies that your exponent, your unknown exponent, which is in this case 3x, is the log. You see, this one is base, so still you put it as base. And then this number is supposed to be in front of your log. Okay? So this is log of 6 in base 5, but I am looking for x, so I multiply both sides. I want to make x alone, so I multiply both sides by 1/3, and this gives me x equals to 1/3 times the log of 6 in base 5, and that's it. That's the exact answer. Okay, we go to number 3. So here you see that I have this situation, and again I can compare this with that equation here. If I compare this one with this one, you see that 9 is playing the role of B, 7 here is playing the role of A, and the whole package in the exponent, 2x plus 4, is playing the role of this x. So if I translate this exponential equality in the form of logarithmic, its equivalent logarithmic equality, then more or less I am done. Yeah, so let me write this here for you. So 7 to the power of 2x plus 4 is equal to 9. So then from here I can conclude that what I have in the exponent, which in this case is 2x plus 4, is equal to a log whose base is just the base as we have here, it's 7, and what you put in front of the log is just 9. But remember, you are still looking for x. If someone asks you what is this is just a number. So if I ask you, can you solve this equation, I'm completely sure you immediately solve it. You move 4 to the right, make it negative, and then you divide by 2. That's the only thing. You can pretend that this is a number. Actually, you don't need to pretend this is indeed a number, but this is written in a fancy way. You might be more familiar with number 5. Of course, everyone is more familiar with 5. But you remember, log of 9 in base 7, it's itself. If I ask you what is this package at the end, you would say that's a number. As simple as that. And then I am looking for x. So you see, you shouldn't get confused because you see log of 9 in base 7 or whatever. So you write 2x is equal to, I have log of 9 in base 7, and I move 4 to the right, it becomes minus 4. But because I am looking for x, I have to multiply both sides by 1 over 2. So then it becomes x. The first term becomes 1 over 2 log of 9 in base 7, and if I multiply a half to minus 4, it becomes minus 2. And that is exact answer for this problem. Okay, let us go to the final part of this problem. Here you know what to do. You see, again, you have this equality. You are supposed to find the exact value for x. So the only thing that you don't know in this equation is this part. Why you don't know this part? Because to understand what is the answer to this part, you need to know x so that you can put it here and then raise 11 to that power. Because x is still not known, I would say that this is your black box, but then immediately everything becomes clear. 2 times this black box which we don't know, plus 5 is equal to 17, yes? So immediately this means that this black box is 12, and then this box becomes 6. So as simple as that. So don't let these things, I don't know, distract you. So you know what to do exactly. So if I want to solve it formally, so I would say 2 times 11 to the power of 1, 3 minus x plus 5 equals to 17. The first thing that I do, I add minus 5 to both sides, or in other words, I move 5 to the right and make it negative. So let me just write it step by step patiently. So then it becomes 17 minus 5, but 17 minus 5 has a better name, and that is 12. And then I still don't know this package, but I know 2 times of that is 12, so it means itself, that package itself is actually 6. So this becomes 11 to the power of 1 minus 3x equals to 6. Now this is exactly comparable with this equation, as you see. 11 is playing the role of this a, 6 is playing the role of b, and this whole exponent is playing the role of my exponent. So immediately I can conclude that what I have in the exponent is the log with the base, the same base 11, but in front of the log I put 6. But I am looking for x, so what I need to do, I move 1 to the right hand side, so it becomes minus 3x equals to log of 6 in base. So this is a little bit similar to b. Let me clean this. This is 6. Okay. And then this is log of 6 in base 11, and then I have minus 1 to make x alone, so I have to multiply both sides by minus a third, yes? So this becomes x equals to minus 1 over 3 log of 6 in base 11, but plus 1 over 3. So if you know probably that I'm an optimistic person, I prefer to write the positive one first. Of course, it is not mandatory at all. So this would be the exact value for this equation. Good. Okay, now let us go to another problem. In this problem, I'm concentrating on calculating the logs, without calculator. And when I say that calculate without calculator, determine the exact value of each one of the following logarithms without using any kind of digital help, it means that in principle it is doable. You don't need actually the calculator at all. So what we have to do, sometimes it is so simple that we can just guess and just do it if you can actually. So here, for example, number 1, this is telling you that can you calculate log of 64 in base 8? When you see a log, actually this is asking you, can you give me a number so that when I raise 8 to that number, it becomes 64? This is so simple that I can just simply guess, of course. So let me just guess it, and then 64 in base 8 is equal to 2. If someone asks you why, you would say because 8 to power 2 is 64, and I am done. So let us go to number 2. Log of 100. So what is log of 100? You know that there is no base written, so if you remember the remark, this means that the base is 10. So this is asking you, can you give me a number so that when 10 is raised to that number gives 100, it's immediately evident that this is also 2. So log of 100 is just simply 2. What about number 3? Okay, so number 3, we want to calculate log of this number, 0.0001. And when we don't write the base, again the base is 10. If you can guess, which I don't think it is hard, that's okay. But if you cannot guess, is there any way to do it more systematically? The answer is yes. You would say that, let me change my color, this would be the solution. I want to find this, so I don't know this value. I call it x. You see, this is not an equation at all. Equation needs an unknown in the setting of the problem itself. You see, there is no track of x whatsoever here, yes? So this is not an equation at all, but I bring in a variable to facilitate, to pave the way that I can go and solve and find this log exactly. So I would say that, okay, let me call it x. Then what happens? Then it means that the base, which is not written, it means that it is 10. It means 10 to this power is equal to that one, and then I will try to find x. So this immediately gives me that 10 to the x is equal to 0.0001. But you already have some experience in solving these equations. We can solve these equations if we can write both sides as the power of the same base. The base here is 10. Is it possible to write this as a power with base 10? The answer is not that hard, because this number is 1 over 10,000, yes? And everyone knows that 10,000 can be written as a power of 10, which is 10 to power 4, but I bring it up, it becomes 10 to power minus 4. And now if I compare this first one with this last one, if I compare this first one with this last one, yes, then I immediately conclude that x is equal to minus 4. Why? Because 10 to the x is equal to 10 to the minus 4. The bases are the same, so the exponents have to be the same, and x becomes equal to minus 4. So if you could not guess, now you don't need to guess. You realize that the log of 0.001 is nothing except minus 4, and that's the exact value for that. Okay, by the way, let me just mention something here. If you go to your calculator, this is also essential to know, there is only one button on the calculator regarding the log. Two buttons. One of them is the natural logarithm that you don't study this, it would be the topic of the next year. Another button is log, log of, and this means that you can always calculate using the calculator logarithms in base 10. If you want to calculate something like this using the calculator, we will come to some ideas how we can do this using the calculator. But for the time being, you can just calculate logs in base 10, and I would recommend you to try on your calculator by punching these logs into your calculator and confirm that you get exactly this number, even though you're not supposed to use the calculator here. It's just for checking yourself. Okay, number 4. Again, I would say number 4 is easy. Might be, if you are a little bit friend with numbers, you can guess, yes? So I want to calculate log of 81 in base 3. So this log is asking you about a number so that when 3 is raised to that number, it gives you 81. I don't think that is hard, so let me just write that number is 4, yes? 3 to the power of 4, 3 times 3 times 3 times 3, it becomes exactly 81. Okay, number 5, sorry. So in number 5, I have the log of 8 in base 4. Okay, I want to calculate that. So let us write it here. So log of 8 in base 4. This is again asking you about a number so that when 4 is raised to that number, it becomes 8. So might be it is not that evident to be able to guess it, so let us use this trick that I used for part 3 again. So it means that I bring a variable in myself, so I want to find this, I don't know, so let me call it x. Then I use the definition of the logarithm. It means that 4 to the x is equal to 8. If I want to succeed to solve this problem, I have to write these numbers in the same base. And immediately, hopefully, you realize that 4 is 2 to the 2 and 8 is 2 to the 3. So this gives you the fact, the thing that you need actually. 2 to the 2 to the x, 2 to the 3. But then 2 to the 2 to the x, it becomes 2 to the power of 2 times x using this formula, yes? I have a to the power of m, another power, and it becomes a to the power of m times n. These are extremely important to remember by heart, otherwise this would be problematic for you. So then on the right hand side you have 2 to the 3, but then on the left hand side I have a power of 2, on the right hand side I also have a power of 2. They are supposed to be equal, so this is not possible unless the exponents are the same. And then because I am looking for x, I have to make x alone. I multiply by 1 over 2, it becomes 3 over 2. So that is what I get. And then it means that, yes, I have now my answer. Log of 8 in base 4 is exactly 3 over 2. Okay, so number 6. Log of 25 in base square root of 5. Okay, so again let us use the trick. If we don't know how to solve it, I call it x and I use the equality. It becomes a square root of 5 to the x is supposed to be equal to 25. But then extremely important formulas. So let me write them here for you. We know that square root of any number a, of course any non-negative number, otherwise it is not defined, is nothing except 1, a to the power of 1/2. And then you also have this, the nth root of a is a to the power of 1 over n. These are in the formula sheet, but this one I also want you to know it's not in the formula sheet. So the nth root of a to the m is equal to a to the m over n. Okay? This is also very important to know. Let me change my color to talk a little bit about this. So what is this one? The nth root of a to the m is equal to. So you know that this means that we have the nth root of a, but a to the m, so let me make it nicer. So this becomes the nth root of a times, for example, a times up to a m times. M times, yes? But then we can write it as the nth root of the first one multiplied by the nth root of the second one up to multiplied by the nth root of the last one. How many times? Again, m times. Okay, but now according to this formula, each one of them can be written as a to the power of 1 over n. So this becomes a to the power of 1 over n times a to the power of 1 over n times a to the power of 1 over n, yes? But then we know the rule. I write a and I start adding the exponents. This is the famous rule. But I am adding the same number 1 over n m times. So this is nothing except a to the power of m over n. So if you're interested to see why this formula is also correct, you can see this according to what I mentioned you here. Okay, so now you see that this is extremely important to remember this. And here I would say that, let me write below it. So this becomes, instead of square root of 5, I write 5 to the power of 1/2 to the power of x, and instead of 25 I write 5 to the 2, but the left hand side becomes 5 to the power of 1/2 times x equals to 5 to the power of 2. So here I am using this fact that if I have a power, another power, then the powers are supposed to be multiplied. So, and then this means that I have two exponents equal with the same bases. Yeah, so this means that this is not possible unless the base of the left one is equal to the base, the exponent of the left one is equal to the exponent of the right one. But my goal is to find x, so I multiply both sides by 2, so x becomes equal to 4. So then it means that the log of 25 in base square root of 5 is nothing except 4 exactly. Okay, so now let us go to number 7. Yes, so let me to manage somehow that I can solve both of them here. Number 7. So number 7 is the log of 1 over 27 in base 3. I think some of you still can guess, but if you can, don't worry. So you just write log. Your number in front of the log is 1 over 27 and your base is 3. If you cannot guess the number, you just use the same trick. And then this means that 3 to the x is 1 over 27, okay? So then now you know that 27 is the third power of 3, so this becomes 3 to the x is equal to 1 over 3 to the 3. Then you bring it up, it becomes 3 to the power of negative 3. And then if you compare these two, immediately you realize that your x is minus 3. And then following that, you say that, okay, the log of 1 over 27 in base 3 is minus 3. And then I put this in a box, hopefully here. Good. And now let us go to the last one in this problem. And that is the log of 128 in base 0.5. Is this base acceptable? Of course yes, because the base has two conditions to satisfy. One of them, the base should be positive. Of course 0.5 is positive, and the other one is that the base cannot be equal to 1, and it is clear 0.5 is not equal to 1. So that's completely an acceptable log, yes? So I want to calculate the exact value of that. So let me just write number 8. And probably this is also a little bit hard to guess, so let us just do it step by step. Log of 128 in base 0.5. So let me call it x. Then this implies that 0.5 to the x is supposed to be 128. Okay, what we can do? If you, of course, are friend with numbers, as I always say, you know what is 128. It's the 7th power of 2. If not, of course, you can still do something. Yes, you can go to scratch paper. If you remember from Math 1C, you can factorize it. Okay, so you can say I divided by 2, it becomes 64. I divided by 2. You know that on the right hand side here you are allowed only to put prime numbers, so that these numbers are divisible by those prime numbers. And if you continue this correctly, always and always you end up with a 1 on the left hand side, and this means that the process is finalized there. So then it becomes 32, divide by 2, it becomes 16, divide by 2 is 8, divide by 2 is 4, divide by 2 is 2, finally divide by 2 as we predicted, it becomes 1. And then you see that 128 is nothing except 2 to the power of 7. And I don't think it is hard for you to understand what is the relation between 0.5 and a power of 2, because 0.5 is nothing except 1 over 2, and 1 over 2 is 2 to the power of negative 1. So now I think everything is ready. So let me rewrite this expression. Instead of 0.5, I put 2 to the negative 1, and instead of 128, I put 2 to the 7. So then it becomes 2 to the power of minus 1 to the power of x equals 2 to the power of 7. But on the left hand side, I have two exponents, again the same formula. You see, I have an exponent, another exponent, so these exponents are multiplied, but minus 1 times x is nothing except minus x, and it becomes 2 to the power of 7. So this implies that minus x is equal to 7, and it means that x is equal to minus 7. And then finally, we write the answer. So the log of 128 in base 0.5 is minus 7. Okay, so you need to improve your skills in calculating logs whenever they have some relations. Whenever what appears in the base and what appears in front of the log, they are somehow related in the exponent form to a one single number, then you can solve this exactly. For example, here, square root of 5 is 5 to the power of 1 over 2, so this is related to 5. Okay, and 25 is also related to base 5, 5 to the 2, so it means that we can solve these problems exactly. Okay, now let me increase the level of difficulty. Okay, determine the exact value of each of the following logarithms without using any kind of digital help. Okay, so of course these are even probably more than level 1 problems, okay, but let us see that we can still solve them very easily. Okay, so number 1, we want to calculate the log of the third root of 16 in base 1 over the fourth root of 8. Yes? So this number is the third root of 16, and this number is 1 over the fourth root of 8. Okay, this is probably very hard to guess, so let us just use the normal trick. So I will call it x, then this means that this number raised to this power will give me this. So then it means that 1 over the fourth root of 8 to the power of x is equal to the third root of 16. Okay? But let me remind you again, so I want to use this formula at the very end. If I have the nth root of some number to the m, you write a here, and then you make a fraction as the exponent. How you write the fraction, what you get here, you put it in the denominator, and what you get here, you put it in the numerator. Okay, so I want to use this formula here. So let us just go to a scratch paper, not a scratch paper, it is also should be also included in the solution, but let me just do it on the margin here. So margin here, so it is a third root of 16, it is the third root. I know that 16 is 2 to the power of 4. Of course, you might say that 16 is also 4 to the 2. How did you know that to use 2 to the 4, not 4 to the 2? Even 4 to the 2 is also 16. The reason is that I am looking a little bit ahead of me. Here I have 8. I know that if I want to write 8 as an exponent, I should write the base 2, because 8 is 2 to the 3, not 4 to some base, to some power. Yes? So this is what motivation by looking a little bit ahead of you. It's clear that it's better to write 16 as a base 2 number. Okay, so then it becomes, according to that formula, it becomes 2. I put 4 in the numerator and 3 in the denominator. That's it. And then I go to the 1 over the 4th root of 8. 8 is 2 to the 3, yes? So it becomes the 4th root of 2 to the 3. But you can write the 4th root of 2 to the 3 according to the same rule, 2 to the power of 3 over 4. And then I bring it up. It becomes 2 to the power of negative 3 over 4. Yes? And now I go back here. Instead of this expression, I put this number. And instead of this, I put this, okay? So this becomes 2 to the power of minus 3 over 4 to the power of x equals to 2 to the power of 4 over 3. But then I have an exponent. After that, I am exponentiated once more. So the rule is to multiply these exponents. So it becomes 2 to the power of minus 3 over 4x. And on the right hand side, I have 2 to the power of 4 over 3. And now I achieved the goal, yes, because I have 2 powers of 2. They are supposed to be equal. So this means that the exponents have to match. So this means that this is equal to 4 over 3. But because I want to solve this problem for x, so let me multiply by 12 to get rid of these denominators. When I multiply 12 here, so 12 times minus 3 over 4, 4 and 12 are simplified, so I get 3. 3 times minus 3 is minus 9, so it becomes minus 9x. And when I multiply 12 here, 4 over 3 multiplied by 12, this one and that one are gone. 4 is 16. But again, because I want to make x alone, so I divide by minus 9, so the answer is minus 16 over 9. So then you can write this, which was not easy at all to guess. Yes, the 3rd root of 16 in base 1 over the 4th root of 8 is equal to a negative number minus 16 over 9. Okay? So the next one might be a little bit scary, but it's not, yes? It's actually very simple. But you need to understand what is the meaning of these consecutive signs of logarithms, yes? So this means that you calculate this log, it becomes a number. And then for that number, you calculate the log in base 4, and you get another number. And then this you get the log of this new number in base 8. So this is something that you need to do step by step. Yes? So, and this is very easy. We can guess everything. And the reason that I brought this up, because I want you to know about these kinds of rules. So log of 8 acts on this package. Log of 4, log of 2, 16. Yes? And I think every one of you can guess. So momentarily forget about what you see here. Okay? Don't confuse yourself. So you have one simple log here and you can immediately answer that. What that answer is, I hope that you can guess correctly. Yes, I need a number so that 2 raised to that number, it becomes 16. It's evidently 4. Okay? So that it means that I was able to do one step. I went forward one step. So it means that I have to copy paste log of 8. I have to copy and paste log of 4, but instead of this whole expression, I can simply put 4. Yes? 4. And I think this is also very simple. Yes? Log of 4 in base 4. It's doable, yes? It's 1. Because I'm asking you, can you give me a number so that 4 to that number becomes 4? The answer is clearly 1. So then it means that this becomes log of 1 in base 8. Even though I will talk about this log of 1 formally later, but this is evident. Yes, can you give me a number so that 8 raised to that number becomes 1? Of course, there is only one number with that property, and that is 0. Yes, 8 to the power of 0 is equal to 1. So the answer actually of this is equal to 0. Okay, now let us go to number 3. This is a little bit, you need to be careful. So first of all, you see that again, this consecutive logs, you now have enough experience. Yes, you know what to do with consecutive logs. So this is a strange number a little bit. You calculate the log of that strange number, it gives you another number, and then by the way, the base is not written, so it is 10. And then what you do, you take another log from that number. Okay. Thing that I want to discuss a little bit before starting the problem is this combination. I want to make sure that you know about this. So let us analyze this. So what you have, let me write with a different color here. Of course, these are parts of the solution, so let me write them with this just the same color. So we have the second root of the fifth root of 10. Okay. So what does this mean? So here, do you remember I told you, so let me write the formula again here in front of your eyes. If I have the nth root of a, you can write it as a to the power of 1 over n. Okay, so I want to use this formula 2 times. Okay, what? So for example, what you can do, can I write something for this one? You would say yes. So consider this is playing the role of a, and then you have square root of a. You can write it as a to the power of 1/2. Okay, but what is your a? A is this package. So this becomes the fifth root. The fifth root of 10 to the power of 1/2. Whole package, yes? But then the fifth root of 10, according to the same formula, has another name. So you can write it 10 to the power of 1 over 5. What I have written so far is just another name for this, but you see that up there I have another power of 1/2, so this means that I have another power of 1/2. And then of course you know that if I have an exponent and I exponentiate it once more, the rule is to multiply the exponent. So this becomes nothing except 10 to the power of 1 over 5 multiplied by 1 over 2. But 10 is just 10. 1 over 5 times 1 over 2 is just simply 1 over 10. As simple as that, yes? So here, if I ask you, what is another name of this? You would say it is 10 to the power of 1 over 10. Okay? And now let us go and try to solve the problem. So what was the problem? The problem has two logs, one after the other. So I have log, I have another log, and then I have the second root of the fifth root of 10. Yes? But now I copy and paste these two logs. But instead of this one, I can write 10 to the power of 1 over 10. Okay? Now, I hope that you can guess the whole number here. This is asking you about a number so that when the base is not written, it is 10. We want to write 10 to some power becomes 10 to the power of 1 over 10. Yes? So it is clear that this is 1 over 10. If not, you go aside, let me try to give it a name. If you don't understand exactly what is going on, whenever you don't know how to guess, you just give it a name. And then, what is the base here? The base is 10, so 10 to the x becomes this number. So then this implies that 10 to the x is equal to 10 to the 1 over 10. It's very simple, yes, because the bases are already 10, and it means that I can immediately conclude that x is 1 over 10. Okay, but this name x was given to this guy, and I realized that x is just 1 over 10. So what I do, this becomes equal to log, but instead of hold that package, I put 1 over 10. And I think it's very easy for you to guess. Can you guess the number? I want a number so that when 10 is raised to that question mark, it becomes 1 over 10. Evidently, question mark is minus 1, yes, isn't it? So the answer becomes minus 1. So the question mark for this problem at the end is just simply minus 1. Okay, now let us do the last problem here. We have 3 consecutive logs with different bases. Here the base is 2, here is the base 3, and here is not written, so the base is 10. So you know, you have enough experience. You have to start from the innermost log and go outward, yes? So let me just write everything in front of our eyes here. So number 4. So I have log, let me see, 2, 3, and 10. And then I have 10 to the power of 81, yes? Okay, so let us again use the same trick to calculate this one. So I call this one x. So I would say log of 10 to the power of 81. Of course, you should be able to immediately guess that, okay? But let us assume that you cannot, okay? In that case, you say that log of 10 to the power of 81 is my goal, so I call it x. Then this would imply that 10 to the power of x is equal, you see, 10 to the power of x is supposed to be equal to this number. So I just put this number here. It becomes 10 to the power of 81. And now you realize that immediately x is 81. So now everything becomes clear. So I will go here and I copy and paste the first 2 logs. But now that I know x is 81, what I do, I write 81 here. But now if I ask you, can you guess something about this? It's extremely simple. 3 to what power becomes 81? Evidently 4. So it means that instead of this expression, I can simply put 4, and then it becomes log of 4 in base 2. Can you give me a number so that 2 to that power becomes 4? It's even much simpler than any one of the problems that we have solved so far, and that is immediately becomes 2. So the question mark here in this problem is nothing except 2. Okay? Okay, now let me give you 2 remarks. Okay, one remark is this. Let me read it for you. Not all exponential expressions can be written in a logarithmic form. For example, minus 3 to the 2 is 9, and that is exactly true. Yes, this is a true statement. This cannot be written in a logarithmic form, because if you remember, I told you that when you have a to the x equals to b, then this would imply that log of b in base a is equal to x. You might say that, okay, minus 3 to power 2 is equal to 9. Let me give the role of a to minus 3, the role of x to 2, the role of b to 9. So you conclude, might be you conclude that the log of 9 in base minus 3 is equal to 2. Yes? This is something that you need to be careful. Not every exponential form can be translated into a logarithmic form, even if the exponential form is true, because when you want to do this, you need to respect the definition of the logarithm. You cannot put a negative number as the base. The number that you put in front of the log should be positive. The number in front of as the base should be positive, but you also have another constraint on the base, and that is the base cannot be equal to 1. The reason behind that is, if you have forgotten, you can go and review what we said in the first video about logarithm part 1. Okay, so be careful. If you see something like this, even though minus 3 to power 2 is still equal to 9, but this is not acceptable. Another remark, which is very important actually, is this combination. Okay, so let me elaborate a little bit here. So this tells you that, first of all, this A, on the right hand side I have just one B. Here, if I want to write it a little bit in exaggerated form so that you can see, A on the left is the base, and log of B in base A is the exponent of this A. Okay, this, if you recognize, this is a little bit smaller, the font is smaller. Okay, so this whole package is the number that you are supposed to raise A to that number. But what is that supposed to be? That's supposed to be equal to B, because that's definition. Yes, if I ask you what is the meaning of log of B in base A, when you say that log of B in base A is x, what does this mean? This means that A to the x is equal to B. Yes, but then you can translate it even more. Yes, here you can take this x away and put this instead, because x and this are the same. So if I change x with what is equal to x, the left hand side remains the same. So remove this x out and put that package. Then what you will have? You have A to the power of log of B in base A, and on the right hand side you have B. So let me repeat. You see, I copied and pasted B, I copied and pasted A, but instead of x I have put this one, so I get this information, and that's exactly this relation, and this is exactly what we're supposed to show. In other words, what was the log of B in base A? Do you remember? Log of B in base A is the number, so that when you raise A to that number it becomes B. Now you are raising A to that number, so definitely by definition it becomes B. Yes? So it's extremely important. So if you have A in the base and in the exponent you have a log with the same base as you see here, then you can get rid of all these things and the answer simply becomes B. It's very handy sometimes. Okay? For example, let us solve this example. Determine the exact value each of the following logarithms without using any kind of digital help. Yes? So how should we should do that? Number one, I want to do it in two different ways. But for the other numbers, there is only one way to do it if you want to do it exactly and using the help of this formula. Okay, so let me write number one, method one. Okay, so the reason that we can solve it in two different ways, I will tell you why. Because log of 27 in base 3, forget about this for the time being. If I ask you, do you know this number exactly? Hopefully all of you will know about it. What is the log of 27 in base 3? It tells you, give me a number, so that when I raise 3 to that power it gives me 27. So it is clear that this number is 3 itself. Okay, so if I want to go forward, I copy and paste this 3, and instead of this log I put 3. Yes, but then if I ask you what is 3 to the 3, you know the answer, it's 27. And you see that it was much simpler to use this rule, because this 3 and this 3 are the same, and you have a log, you can get rid of all of them, and what is left for you is 27. The reason that this method works in this case, because you were able to calculate this exactly even without calculator, and you got 3. Okay, but method 2, I want you to use the theorem, or the definition, or the formula. So 3 to the power of log 27, if you see this, you don't need to do any of these. You can simply say 27, because now 3 is playing the role of A. You see 3 and 3 are A and A, and then 27 is B. So the answer should be B, as simple as that. But for number 2, for example, method 1 does not work. Because if you ask me, do you know this number? I would say no. I don't know the exact value. Log of 7 in base 2, it means that it's a number, so that 2 to that number it becomes 7. Of course, I know that this is bigger than 2 and it is smaller than 3. That's it. I don't know more about it. But the problem asks me about the exact value, and that's not an exact value. So it means that there is only one way to do it, and that is exactly using this formula. Okay, so if I want to solve that, 2 to the power of log of 7 in base 2, you just make sure that the left hand side is exactly, the pattern of the left hand side matches with this pattern. Yes, this A is 2 in this problem and B is 7, so the answer becomes B, so and that is 7. Okay? Now number 3. What can you do for number 3? Don't be in a hurry. So let me make it a little bit smaller. So 5 to the power of 3 log of 8 base 5. How can I simplify that? Don't be in a hurry and then say that, okay, I cancel these things, it becomes 8. 8 times 3 is 24. No, that's completely wrong. In mathematics, you should follow exact rules. This rule, this pattern is not exact pattern here. Yeah, I have an extra 3. Okay, but I have an extra 3. I need to deal with that. When I have an extra 3, it means that the pattern is not exactly this. If I want to do it correctly, I have to exactly follow the prescribed patterns. Okay, so for example here, what can I do? I can write it in this way. I can write 5 to the log of 8, 5, and then raise it to power 3. If someone asks you why, I would say that I am using this very famous formula again. A to the m to the n is nothing except that a to the m times n. Yes? Okay, if I ask you what is another name for this, you would say that I have 5 to some power, let me call it m, to another power, let me call it n. So it becomes 5 to the power of the product m and n. M and n becomes exactly this if I multiply them. But what is the benefit of that? The benefit is that this is exactly the pattern. You see, if you compare this one in this with that one, that is exactly the pattern. 5 is playing the role of A and 8 is playing the role of B. So the answer inside the pair of brackets is 8. And then of course I have a power of 3. You see, the answer is 8 times 8 times 8, which is 512. If you have done it in that way, you multiply 3 by 8, you might get 24. So be careful that you are following the patterns exactly. Okay, so finally number 4. What can I do with number 4? This is different. Hopefully you have enough experience what to do that. I would recommend you to pause the video at this point and try to solve the problem yourself first here. Okay? And then see what would be your answer. So if I am right, what you get should be 75 at the end. Yes, let me double check. Yes, you should be able to get 75 at the end. So I would recommend you to pause the video and try to solve this problem yourself first. Okay, now that you are back, might be you know what to do. So here, 4 to the power of, log of 3 in base 4 and plus 2 times log of 5 in base 4. So what can I do? I can write it as 4 log of 3 in base 4 multiplied by 4 to the 2 times log of 5 in base 4. Which formula I am using? I am splitting this combination. Yes, a to the m plus n can be written as a to the first one multiplied by a to the second one. Yes. Okay, so you see this I split this exponent to the first one times 4 to the second one. This you don't have any problem. That's exactly the pattern, so it becomes 3. This is because of this 2, that's not exactly the pattern, but you remember the trick from the previous step. So then it becomes, let me write it here, so this becomes equal to, the first one as I told you is 3, but for the second one you have to rearrange it a little bit. So I would write it by the experience from the previous part. I would write it like this, and then I would write to the power of 2, yes? Because 2 and this will be multiplied and I will get this one. But this now again is exactly the same pattern. So this becomes 3 times 5. This expression is 5, and then I have a power of 2. So then it becomes 3 times 25, and as I mentioned before you start, the answer is supposed to be 75. So the question mark here is nothing except 75 exactly. So you see, you still can calculate a lot of things exactly without the use of calculator if you know how to use these formulas effectively. Good. Now let me just mention this theorem formally, and then this would be the end of lesson today. Okay? So, and I told you that in the book they talk about rules, but I think the best, more formal word for the rule is theorem in mathematics. Okay? So if a is positive and not equal to 1, log of 1 is 0, and log of any number in its own base is equal to 1. Yes? Log of 1 in any acceptable base, by any acceptable base I mean positive and not equal to 1, then the answer of log of 1 in any acceptable base is 0. The log of any number in its own base, if it satisfies the condition of being a base, of course, it becomes equal to 1. And any theorem needs a proof, so I need to motivate why this works. Okay? But this is extremely simple. I just talk about it orally. Why this formula is correct? Because let me just write it for you, no problem. So log of 1 in base a is equal to 0. What is this equivalent to? You remember, it is equivalent to saying that a to the 0 is equal to 1. But we know that this is true. So this implies that this one is also true, and I am done. And then the same story for the next one. So log of a in base a is 1 if and only if this is equivalent to saying that a to the 1 is a, but we already know that this is true. A to the 1 is definitely equal to itself, and this implies that this one is also true. Yes? So this means that, for example, log of 1 in base 3, you don't need to do calculation. Whenever you see log of 1 and the base is acceptable, the answer is 0. Log of 1 in base square root of 2, that is also 0. But any log of any number in its own base, it doesn't matter how complicated the number is, you get just 1. If I say log of 10, what's the number? You immediately say 1, because when you don't write the base is 10, and then you are looking at 10 in its own base, so the log is 10. Okay, I will stop actually here. I don't want to go any further, and then we will continue more interesting theorems regarding